Okay, picture this. You're trying to find a specific name in a randomly shuffled phone book. Sounds like a nightmare, right? Without any sort of order, you're literally stuck checking every single page one by one. And well, this exact scenario highlights a completely foundational need in computer science, sorting data. So welcome to this explainer. Today we're going to totally demystify two classic algorithms used to solve this exact problem, bubble sort and selection sort. Let's get into it.
Here's our roadmap for this explainer. First up, why sort data? Then we'll break down the bubble sort method, followed by the selection sort method. After that, we'll be comparing complexity, and finally, answering the big question, which algorithm wins?
All right, kicking things off with section 1, why sort data, the foundation of efficiency.
So, what exactly is a sorting algorithm? Well, at its core, it just arranges data into a specific required order, like ascending from smallest to largest, or descending. This is absolutely crucial because a sorted list can be searched infinitely more efficiently than an unsorted one. It essentially turns a chaotic, messy list into something a computer can process in a snap. Now, looking at this from a high level, these two strategies take very different paths to get to that same organized result. Bubble sort is all about pushing the largest values to the right by constantly comparing adjacent numbers. Selection sort, on the other hand, it prefers to hunt down the absolute minimum value and place it right at the front.
Moving right along to section 2, the bubble sort method, subtitled Pushing the Largest Values. So how does bubble sort actually work? The mechanics here are surprisingly simple but highly active. It repeatedly compares adjacent neighbors in a list. If those two values are in the wrong order, boom, it swaps them. By doing this, it ensures that the largest unsorted value literally bubbles its way up to the right side by the end of each pass. You just keep repeating these passes over the dataset until the whole thing is perfectly sorted. Let's actually trace this out on a real dataset to see it in action. Imagine we have the numbers 7, 3, 5, and 1. In pass 1, we look at 7 and 3. 7 is larger, so we swap them. Next, 7 and 5. Yep, swap again. 7 and 1. Swap. Notice how the number 7 aggressively pushes its way to the very end of the list in just a single pass. It is successfully bubbled to its correct final position. Now, here's a massive tip if you are tracing this out for an exam. You have to update the whole list after every single comparison, not just at the end of a full pass. So, moving into pass 2, 3, and 5, they're fine, no swap. But 5 and 1 definitely need a swap. By pass 3, swapping 3 and 1 finishes the entire job. And since the right side is already getting sorted from our previous passes, we actually need fewer and fewer comparisons as we go.
Okay, let's switch gears. Section 3, the selection sort method, hunting for the minimum.
Instead of constantly swapping with noisy neighbors, selection sort kind of plays the long game. It patiently scans the list, it starts at the first unsorted position, searches the entire remaining list to hunt down the absolute smallest value, and then locks it into place with just one swap. After that, it simply shifts one place to the right and repeats the whole process.
The really cool outcome of this strategy is that once that minimum value is located and placed at the front, that specific position never needs to be checked again. The algorithm is steadily, consistently shrinking the area it needs to search.
Tracing our original dataset again, 7, 3, 5, 1, we see selection sort gets the job done in a radically different way. In pass 1, it scans the whole list, finds the number 1, and makes one massive swap, yanking the 1 to the front and tossing the 7 to the back. Because the remaining numbers happen to already be in relative order, it performs exactly 0 swaps on the remaining passes. It's just confirming the 3 and the 5 are in the right spot. Done.
All right, on to section 4, comparing algorithm complexity. Time and space, also known as Big O.
So both of these algorithms actually share a worst-case time complexity of O of n squared. Basically, this means there is a quadratic growth in the time they take as the dataset gets larger. And here is a huge exam tip for you. Do not just state O of n squared. Always, always explain why, which in both cases is due to the nested passes repeatedly scanning the data. You essentially have loops inside of loops comparing many pairs of elements. While both are comparison sorts with quadratic worst-case times, their key difference is in the action itself. Bubble sort is incredibly swap-heavy. I mean, if values are very out of place, it will perform swap after swap after swap. Selection sort, conversely, favors way fewer swaps, placing items directly. But, and this is a big but, it still makes an enormous amount of comparisons to find those minimum values during every single pass. Let's break down the data. Memory-wise, they're both brilliant. They have an O of 1 space complexity because they sort in place using minimal extra memory. But look closely at the best-case time. An optimized bubble sort can actually hit an O of n best-case time if it uses a flag to stop early on a list that's already sorted. Selection sort, on the other hand, stubbornly has to search the remaining elements no matter what, keeping its best case stuck at O of n squared.
Which brings us to Section 5, which algorithm wins? The final showdown.
Starting in Bubble Sort's corner, it is a fantastic teaching tool. It's super easy for beginners to trace, and it's absolutely great for nearly sorted data thanks to that early stopping optimization trick we just talked about. But its excessive swapping is a fatal weakness for truly messy data, which leads to incredibly poor efficiency on anything larger than a tiny data set. Now, in Selection Sort's corner, it has its own unique benefits. It easily avoids that heavy swapping penalty that Bubble Sort suffers from, and it's also wonderfully easy to trace out on paper. However, its stubborn insistence on checking every single remaining value, even if the data is already sorted, makes it highly inefficient. Quite frankly, it's totally unsuitable for large-scale applications. At the end of the day, the judgment comes down to scale. As our source material points out, for tiny lists and teaching situations, either algorithm is perfectly fine. But for real-world, large data sets, both are completely unacceptable. You'd absolutely want something far more efficient, like a merge sort or a quick sort, to handle that kind of load. Before we wrap up this explainer, I've got a bit of a puzzle for you to chew on. If both of these algorithms are fundamentally O of n squared in their worst-case scenarios, why exactly does an optimized bubble sort pull ahead of selection sort on a list that's mostly sorted? Grab some paper, trace it out for yourself, think about how those loops actually run, and keep exploring.